Recording.
So, hello everyone. Today we will be presenting our term project, which is the application of In-situ XRD in structural transformation of cathode materials for lithium-ion batteries. So, the lithium-ion batteries are rechargeable electrochemical energy storage devices that consist of five main components: the anode, the cathode, and the electrolyte, the separator, and the current collectors. And among these components, the cathode is the most critical one because it determines the battery's energy density, operating voltage, and structural stability. Cathodes are usually lithium-containing transition metal compounds, and their electrochemical behavior is strongly related to their structural crystal structure. And the most common structural frameworks include layered, spinel, olivine, and disordered rock salt. In layered structures, oxygen forms an FCC lattice. Lithium and transition metals occupy octahedral sites, and the oxygen layers are stacked in ABC sequence. And in spinel structures, oxygen ions are also arranged in FCC framework, where lithium occupies the 8A tetrahedral sites, while manganese occupies the 16D octahedral sites. In olivine structures, the oxygen forms a distorted hexagonal close-packed framework where lithium and iron occupy distinct octahedral sites, and which are connected by a rigid phosphate tetrahedral network. And finally, in disordered rock salt structures, the framework can be described as a layered structure with randomly distributed cations. Lithium and transition metal ions are randomly arranged, so the distinction between lithium layers and transition metal layers is not clearly defined. And so, during battery operation, these crystal structures do not remain static. They undergo lattice changes, phase transition, and sometimes symmetry modification. So, we can study those structural transformation using ex-situ and in-situ XRD. On the left, ex-situ XRD follows a snapshot approach where the battery is first cycled, then disassembled, and the cathode is measured separately. This method provides structural information at specific states of charge, but it may miss the intermediate phases. On the right, the In-situ XRD allows us to monitor the crystalline structures in real time during charge and discharge. And in this process, the battery is placed in a specially designed X-ray transparent cell, and the diffraction patterns are collected continuously, which enable us to directly observe the dynamic transformation, which is essential for understanding how cathode materials behave during electrochemical cycling. So, when a lithium-ion battery charges and discharges, lithium ions move in and out, and during that, the lattice parameters change, bond lengths shift, and in some cases, entirely different crystal phases can form. This transformation can proceed either through a solid solution mechanism, where composition changes continuously, or through a two-phase reaction, where two distinct phases coexist. Looking at the diagram on the left, on the top, we can see clearly that starting from a fully lithiated state, the materials begin as a single-phase lithium-rich region shown in red, and as the lithiation proceeds, we enter a two-phase region in the middle where lithium-rich and lithium-poor phases coexist within the same electrode. And finally, when most lithium has been extracted, the material returns to a single-phase lithium-poor region shown in blue. The voltage profile below reflects this behavior, and the structural changes directly determine the battery for performance, capacity, cycle life, and voltage behavior, all dependent critically on how the phase transformation proceeds.
And let's move to the example. For the first example is LFP or iron or lithium iron phosphate has become widely used in lithium ion battery for EV because its long cycle life, excellent high rate performance, cost effectiveness, and non-toxicity and safety advantages. LFP is an olivine type cathode material in which lithium ion diffuse through one-dimensional channels. Because lithium transport is restricted to one-dimensional pathway, the reaction during charging often starts locally inside the particles and then propagate through the materials. During charging, the lithium ion are extracted from the LFP cathode structure and the material transform into the iron phosphate or FP structure according to this reaction. In general, high-rate battery performance is limited by lithium diffusion. When a phase transformation occurs, the reaction is also limited by nucleation and phase growth. Therefore, material without phase transformation are usually expected to perform better at high rate. However, LFP is a special case, even though it is a two-phase material that transform between LFP and FP, it still shows excellent high rate performance. So the question is, why can LFP operate at high rate despite being a two-phase materials? This question motivates the use of in-situ XRD to study the structural evolution during battery operation. And this figure shows in-situ XRD contour plot result during high-rate cycling, and the x-axis represents 2 theta and y-axis represents time in second running from 0 to 2500 seconds during charging and discharging process. Color represent intensity, where red and yellow is high intensity and blue is low intensity. As expected, the LFP peak decreased while FP peak increased when charging, indicating phase transformation. However, additional diffraction intensity appears between the two peaks, like this. And this is the signal of an intermediate phase that lattice parameter fell between those of two equilibrium phases, something that should not exist under ideal two-phase reaction behavior. And this figure zooms into individual XRD snapshot stacked against the voltage profile on the right. You can see in the pattern A, starting point before charge, all FFP peaks are perfectly symmetrical, sharp, no broadening, and this present pure stoichiometric LFP, no FP peaks are present yet. And for the pattern B and C, early stage FP peak begin to appear weakly, and LFP peaks start to decrease in intensity. No obvious asymmetry is visible yet. And for the pattern D is in medium chart. First key observation is for LFP at this plane and LFP at this plane begin to show asymmetry broadening toward a higher angle, meaning the right side of peak start to tail out and lose symmetry. And this indicates that some LFP particles have had lithium partially extract, but not yet fully. Their lattice constants are slightly smaller than stoichiometric LFP, causing a slight shift toward higher angle. And for pattern F and G during the discharge, most critical observation. This is where asymmetry is most severe across the entire figure, and the FFP at 200 and FP at 200 are connected by continuous positive intensity band with no gap between them, meaning particles with all intermediate composition exist simultaneously. This is the clearest evidence of non-equilibrium solid solution. And the last pattern is pattern R. After P peak do not fully recover their original position after the 2 cycles. All the selected peaks shift toward higher angle and broaden. It means incomplete lithium reinsertion and a residual lithium deficient solid solution at high rate. And if we compare the 3 current rate, we can clearly see a difference in the diffraction pattern. At 5C rate, FFP peak in the bright color gradually fade, and while FP peak this grow and then reverse on the D chart, and the gap between LFP and FP peaks remain mostly dark with mean visibility gap is still clearly defined, and reaction proceeds largely as a conventional two-phase process. And however, when the rate increased to 10C and 20C, we start to see the diffraction intensity appear between the two peaks like this. And the most important case is 20C. Here we can see the color become continuous between the LFP and FPP position instead of two separated peaks. The diffraction intensity spread across the entire region, and these continuous intensities indicate that the lithium composition changes continuously, which means the reaction proceeds through the uh, solid solution pathway than a simple two-phase reaction. And this is what all of previous study observed. Since we use the XC2 XRD, only the three snapshot that we can see. The first one is FFP, and after that you just see the FP appearing and more FP particles. Every particle seen is always a pale phase, no mixed color, and no intermediate state, because the transient state had already disappeared before measurement. But for the in situ, you can observe the transient non-equilibrium state, and it always visible only in situ because it disappears within minutes once current is removed, and ex situ never capture this mixed color. And now let me give you another example of how phase transformation affect battery performance, this time with lithium and manganese-rich cathode materials, also known as LMR. Looking at the capacity comparison, you can see that the LMR have higher capacity, exceed 250 milliamp hour per gram. This make it a very attractive candidate for next generation battery. And for the structural, FMR is a composite materials. The first one is a layer trigonal structure with three R3 bar M space group and layer monoclinic with C2/M space group. And this confirmed by XC2XRD that you can see in here. You can see the black color is the main phase of R3 bar M space group, and this color is the second phase of this structure. However, despite the high capacity, LVMR has a serious problem shown clearly in the voltage profile like this. You can see if the cycling continuous from cycle 1 to cycle 36, both of voltage and the capacity fade significantly. And the quick question is this degradation caused by phase transformation? And the answer is yes. If you can see it clearly in this in situ pattern. This in situ pattern observe the peak position during cycling. You can see this contour plot. We can observe that some peak shift continuously during the charging and discharging, indicating lattice parameter changes. And now the most important finding, look at the normalized XRD pattern in the bottom. After the first 1.5 seconds, only rhombohedral peaks is present. But after 16 seconds, a new phase or new spinel peak appear, and it grows stronger after 36 seconds. So you can see that it's because of the phase transformation caused the volt and capacity drop. And this temp image confirm this directly. As you can see in this figure, this pristine material before charging, you can see the empty lithium ion channels, and after 1 second, the lithium ion migrate into the layer structure like this. And after 10 seconds, is reconstruction layer and is blocking lithium transport and this structural evolution from layer to spinel and rock salt. And while controlling this phase transformation remain one of the central challenges for LMR cathode.
Advantages to in-situ X-ray diffraction. X-ray diffraction provides detailed data on the average crystal structure. It is suitable for in-situ operations. It's widely used to monitor phase transformations. The experiments are easy to design compared to other X-ray techniques. The enhanced performance provided by synchrotrons is useful for greater penetration power, shorter measurement times, and superior signal-to-noise ratios. And there's detailed atomic level structural information that can be extracted from the diffraction patterns. Onto the limitations of X-ray diffraction. There is limited utility for amorphous materials. It really is only effective for long range order crystalline materials. It has let's see, it's insensitive to some of the lighter elements like hydrogen and lithium, and there is conventional X-ray powder diffraction provides a powder average over a large spatial range, which can obscure local structural changes or the reaction throughout an electrode. There is lower spatial resolution than SEM or TEM, and there is a risk of the beam damage from the synchrotron. This is not so much of a concern for lab source. On to the next slide, you will see that where X-ray diffraction falls short, there are other techniques for imaging that will fill those gaps and correct those weaknesses. Thank you.